Okay. I think we're good. My screen should be visible.
Yeah.
Okay. All right. Let's get started. So I'm Ben Carver, and today I will be defending my thesis, Wukong, a fast, cost-effective, and easy-to-use serverless DAG engine. So first, I will begin with some background information before discussing the three different versions of Wukong, the framework I developed for my thesis. In my discussion of Wukong, I will go over some results from our evaluation as well as the framework's design. And I will conclude my presentation by summarizing the key contributions and discussing some of the future work. So to begin, Python has become ubiquitous for its use in data analytics. There are a growing number of libraries that are reaching maturity, and this is allowing R and Scala users to utilize the flexibility and performance of Python without sacrificing functionality. For example, Dask is one of these libraries, and Dask automatically parallelizes Python written data analytics code. And this code often uses these other libraries I have listed here, pandas, numpy, scipy, and Dask can parallelize workloads on a single machine or across an entire cluster. Next, we have DAG-based workflows. So data analytics applications can be modeled as a directed acyclic graph-based workflow. In this DAG representation, the nodes represent fine-grained tasks, and the edges represent dependencies in between these tasks. And these diagrams here are just sort of what these DAGs might look like if you were to represent them visually. So we have serverless computing. In recent years, serverless computing has emerged as a new cloud computing platform, and serverless computing allows developers to create applications composed of individual fine-grained cloud functions. Um, One of the appealing aspects of serverless computing is that the service provider is the one who provisions, scales, and manages resources. This relieves these typically tedious and sometimes difficult tasks from users. And serverless computing also offers a pay-per-use pricing model with a fine granularity. In the case of AWS, it's 1 millisecond. And this is attractive in particular because you only pay for the resources that you use. So serverless computing enables a new way of building and scaling applications and services. Developers can break these traditionally monolithic server-based applications into finer-grained cloud functions. These cloud functions will just execute user-defined code for a short period of time. They're ephemeral. After executing the code, they will be reclaimed by the cloud provider. So a common example that's used to illustrate how serverless computing works is shown in this diagram here. So a user will upload, let's say, some images to AWS S3, which is a cloud storage platform. And uploading these pictures will trigger the invocation of a serverless function. And this serverless function will take these images that the user uploaded and do some sort of processing on them. So it could crop them, it could resize them, it could do whatever. And after processing the images, the serverless function will write the images back to S3. And this all happens automatically, and it's managed by the cloud provider, so the user doesn't really have to do anything. Here, we have a quick example of how developers and users really use serverless computing. This to further illustrate how the platform works. So let's say we have a developer here. Let's call her Alice. She wants to make a serverless function. So she will write a simple Python function. She'll define a handler. This is sort of the entry point into the serverless function. This is what gets executed. She'll define this handler and she'll publish it on AWS. And now clients over here, clients can invoke the function in a number of different ways. For example, an HTTP request. If they invoke the function with an HTTP request, it'll execute and return some result to them. And that's basically how it works. It's fairly simple. So serverless computing is well suited as a platform for DAG workflows. The auto-scaling property of serverless computing can accommodate these short tasks and bursty workloads that you generally find in these data analytics applications. And the pay-per-use pricing model of serverless computing is very appealing because it keeps the price of these short tasks low. Again, there's a fine granularity, so you're only paying for what you use. You also don't get charged for the startup time or the shutdown time. So the framework, in theory, if it's designed correctly, can be fairly inexpensive and still deliver good performance. So this brings us to my thesis statement. Serverless-oriented parallel computing frameworks can support fast and cost-effective DAG-based parallel computation workflows that are easy to deploy and manage. And in terms of achieving this thesis statement, there are three primary challenges that I identified. The first of which is the challenge of rapid scheduling and scaling. So there's sort of a question of how can we scale up to and schedule tasks across thousands of serverless functions very quickly and efficiently. The second challenge is that of excessive data movement. So we need to reduce the costly data transfer that might occur between serverless functions while they're executing this workload. Workloads typically generate intermediate data, and this data has to be moved back and forth between the functions, and this can be expensive. So we want to reduce that as much as possible. And the last challenge is making the framework user-friendly. So in particular for people who don't necessarily have a lot of experience with AWS, there's kind of a steep learning curve. So if we were to make a framework that people could actually use, it would need to be, fairly user-friendly and fairly intuitive, not much management on the part of the user. And to sort of motivate these challenges, we have these two plots on the right. So looking at the first plot, this shows the time it takes for numpyren and pyren, they're kind of built upon each other. It shows the time it takes for numpyren to scale up to 10,000 concurrently running executors. And as you can see in the chart, it takes almost 2 minutes to do so. And ideally, a serverless execution framework could scale much more quickly than this. It should be able to take advantage of the high elasticity of the platform and scale to a large number of executors in seconds, not minutes. And similarly down here, this shows the amount of data that is read and written during a matrix multiplication workload. I think it's just a 10,000 by 10,000 matrix multiplication workload here. So this input column shows the size of the input data, and the final result is the size of the data that was generated by the workload. And these read and write columns show how much intermediate data was read and written during the workload's execution. And as you can see, even though the input size was only 10 gigabytes and the output was only 5, there are still hundreds of gigabytes of data read and written during the workload's execution. And this excessive data movement results in very long end-to-end execution times. It causes a greater cost to be incurred. And ideally, a serverless framework could be designed to avoid this read and write augmentation. So with all of these challenges in mind, we can say that naively porting a serverful parallel computing framework to a serverless computing platform will not satisfy the thesis statement. A serverless computing framework will not necessarily care about traditional metrics used by execution frameworks such as load balancing and cluster utilization, and it does not perform well with traditional scheduling techniques. And that brings us to a brief discussion of the two main traditional scheduling approaches used by existing serverless platforms. So there's a queue-based master worker approach and a master directly invoking worker approach. So in this first approach, there is a centralized queue, and the central scheduler, the master node, will submit tasks for execution to this central queue, and the serverless functions will just retrieve tasks from this queue to execute them. And the issue with this approach is that the centralized queue can become a bottleneck, and keeping these executors running in the background so that they can retrieve tasks as they're added to the queue can incur significant cost. We also have the second approach. In this approach, the centralized scheduler, the master node, directly invokes functions, and it passes the tasks directly to these functions to be executed. And the issue with this approach is that the centralized scheduler can become a major bottleneck. There can be substantial scheduling overhead and processing overhead, especially as it's retrieving results from the serverless functions. This can incur significant overhead when it comes to managing all of the connections and whatnot, and it ends up being fairly slow. So this is where our framework Wukong comes in. Wukong is a serverless-oriented, locality-aware parallel computing framework. It distributes the work of a centralized scheduler across many serverless executors, greatly improving performance. And its design enables tasks to be scheduled and executed concurrently, and this reduces resource contention and provides automatic resource elasticity and cost effectiveness. So on the right here, we have a diagram that shows the architecture of Wukong, and I'm just going to quickly run through what a job might look like as it propagates through all of Wukong's components. So first, a user will submit some code, like a Python application, to the client interface of Wukong. Client interface will pass this code into the DAG generator, which will use Dask, the framework I briefly mentioned at the beginning of this presentation, to generate a DAG. And this DAG is passed to the schedule generator, which will partition this DAG into a bunch of subgraphs by performing depth-first searches from each of the leaf nodes. These leaf nodes will then be assigned to serverless Lambda functions by the initial task invokers. They will invoke the functions. They will pass like the task metadata, the task code to these functions. The functions will begin executing the code. Once they're invoked, they'll execute the code. They will invoke new Lambda functions themselves to execute downstream tasks. And what the executors do is they take the tasks in the subgraph that they were assigned and they walk through that subgraph, executing them one after another. And this enables the executors to accumulate a local cache of intermediate data that they can then use as the workload progresses. And this greatly reduces the need to transfer this intermediate data over the network. And this helps to resolve this that read-write issue I mentioned earlier with NumPy run. Sometimes though, they do have to write data to, they do have to send data to each other. And when they do that, they have to write it to the intermediate data store in the storage manager. They also store task metadata here. They use this to coordinate who executes downstream tasks and whatnot. And as they finish final results, they are returned to the subscriber process, which will then give these results to the user. So now I'm going to talk about how task scheduling works in Wukong. In order to efficiently schedule tasks, Wukong uses two methods of scheduling, static and dynamic scheduling. Static scheduling, the input DAG is partitioned into subgraphs, and we call those static schedules. Each static schedule is assigned to a serverless executor, and the executors use what we call dynamic scheduling to enforce data dependencies and cooperatively schedule these tasks found in multiple schedules. So this chart on the right here shows a very simple input DAG and how it would be partitioned into these two static schedules. And to illustrate how the rest of this task scheduling works, I will quickly walk through a few examples of how this particular DAG would be executed. So the program that will be turned into this DAG is given to Wukong and converted into the DAG. The schedule generator will partition this DAG into static schedules, and each of these static schedules will be assigned to a serverless executor by Wukong. Once the executors have their static schedules, they will begin executing tasks contained within their static schedules. So we have two executors here, executor 1 and 2. Executor 1 will execute tasks A and C, while executor 2 will execute tasks B and D. After tasks C and D have been executed, the executors will need to cooperate to decide which of the two will execute task E, as task E resides in both of these static schedules. If it were decided that executor 1 would execute task E, then executor 2 would write the task inputs that it has for task E, which in this case is task D. It would write that information to the intermediate storage, and executor 1 would be able to retrieve it from there. So I would also like to walk through a few of the common operations that we have in Wukong. There are fan-ins and fan-outs. The first thing we'll go through is a fan-in operation, just so we can see how this cooperation works. In this case, we have a DAG with 3 leaf tasks, A, B, and C, and they all fan into a task D. And we have these 3 executors here. So when executor 1 finishes executing task A, it'll increment a counter in the intermediate storage that it corresponds to task D, and this counter is used to determine when task D is ready to execute. Essentially, when the value of this counter is equal to the number of input tasks to task D, that's when task D is considered ready to execute. So when the value of this counter is equal to 3, D will be ready to execute. A is finished, it writes its status storage, it increments the counter. Let's say executor 2 finishes executing C next. It will write its data intermediate storage and increment this counter, which is now 2. Finally, executor 3 will finish executing task B. It will increment the counter. It'll see that task D is ready to execute. So it will avoid this write operation and it will execute task D itself. We also have a fan out operation here. So we have a task A that fans out to tasks B, C, and D. So what will happen here is executor 1 will invoke 2 additional Lambda functions to execute tasks C and D, while it will execute task B by itself. In theory, it could invoke a Lambda function for B and execute C or D locally. It just sort of depends on the order in which it analyzes the downstream tasks. but essentially it will invoke downstream executors for all but one, and it'll execute that one locally. So at this point, I've covered most of Wukong 1. Everything that I've said about Wukong 1 applies also to Wukong 2. The key takeaway here from Wukong 1 is that its decentralized scheduling technique enables it to rapidly schedule tasks across hundreds or thousands of executors, and this directly addresses the first challenge I identified at the beginning of our presentation. However, Wukong 1's performance was hindered by excessive data movement. We found this to be the case in our evaluation, indicating that the second challenge I identified has not yet been resolved. So this is where Wukong 2 comes in. This is where we developed some optimizations to address the second challenge. There are two main techniques we identified or implemented in Wukong 2. The first is called task clustering. With task clustering, we eliminate the intermediate data transfer that's normally necessary by executing all of these downstream tasks locally. And the second technique is delayed I/O, in which we delay performing intermediate data transfer until downstream tasks are ready to execute. Then we perform task clustering on specific tasks. And to illustrate what all this means, I have two quick examples here. So looking at the diagram on the left, let's say task A's output is large, meaning we would like to avoid transferring its data over the network if at all possible, because it will be an expensive operation. What we can do instead of writing A's data to intermediate storage is cluster tasks B, C, and D onto the same executor that executed A. In doing so, we avoid the write operation of A's data and the 3 read operations that B, C, and D would have had to perform, or at least 2 if A executed one of them locally, like it normally does. Delayed I/O is kind of similar. It's more like a special case of task clustering. Once again, we just consider A's output to be large. And we see that we have a task D downstream as well as a task C. Now, ordinarily, A would just see that it has 2 downstream tasks, and it would write its data to intermediate storage and try to execute one of them. But we'd like to avoid writing this data if at all possible. So what A will do is, instead of writing the data, it'll just wait. It won't increment D's dependency counter. It'll just wait until it sees that B has finished executing. Once it sees that B is finished executing, and C is finished executing locally, it'll execute task D. So it just sort of waits. It doesn't tell anybody that it actually has task A's data. It just waits for everything else to finish. And in doing so, this actually speeds things up substantially, as we'll see later on. The read and write operations for large data in particular are just extremely expensive. So this actually makes a fairly large difference. So next, we'll go through some of the results of the Wukong 2.0 evaluation. We implemented Wukong 2.0 in 12,000 lines of Python code, and we compared Wukong 2 against Dask Distributed, which is a serverless Python data analytics framework, and NumPyRen, a state-of-the-art linear algebra framework. We compare against Dask because Wukong, like I said, uses Dask to generate its DAGs, so it's using the same exact input, and it actually executes the same code. So it's a fairly close comparison in that sense. And NumPyRen just happens to be the most closely related serverless framework available. And we had 2 goals with our evaluation. The first of which was, can a serverless framework provide competitive performance against a serverless framework? And the second is, how does Wukong compare to related state-of-the-art serverless frameworks? And this slide shows our experimental setup. I go over this in the thesis in greater detail, so just refer to that if you want a deeper explanation. So the first chart we have here is tall and skinny QR decomposition. So what we see here is just the results for Dask, and we actually used 2 Dask configurations. We used a 1,000 worker cluster where each worker had 2 cores, and a 125 worker cluster with each worker having 16 cores. And we did this because the 1,000 core cluster, each worker is sort of configured to resemble a Lambda function. So the power of each individual worker is more related to Wukong, and the 125 worker cluster represents a more realistic configuration. We also compared against 2 configurations of NumPyRen, one that used S3 for intermediate storage and one that used a single instance of Redis. We chose S3 because Wukong, in its true form, uses a scalable intermediate storage layer. And we also configured Wukong to use a single instance of Redis as well, just to sort of account for the differences in data storage and intermediate data storage between the 2 frameworks. We didn't want that to be the leading reason as to why the performance might have differed. So we tried to control for that by comparing the two using different intermediate storage systems. So here the red arrows are pointing to the two bars representing Wukong. Dask outperformed both of the configurations of NumPyRen, particularly for the smaller problem sizes. And as the problem size increased, the gap between NumPyRen and the 1,000 worker Dask cluster began to decrease. But by the 8 million problem size, the Redis version of NumPyRen actually failed to complete any further workloads. And the S3 version also failed at the 33.5 million slot, so it just could not complete the workload. It either failed with an error or it never finished after like 30 minutes to an hour. And you can monitor the progress, and the progress had stopped, so it couldn't continue. As for Wukong, we can see that Wukong outperformed NumPyRen by a fairly considerable margin for all problem sizes. Wukong also outperformed the 1,000 worker Dask cluster for all problem sizes above 131,000. But Dask outperformed all of the 125 worker Dask outperformed all of the other frameworks. This is largely due to the fact that the workers in that configuration are very powerful and they have much higher network capabilities and more main memory, so they can store more data locally. Overall, they just have much better hardware specs than the other frameworks, and that makes a big difference. As for the I/O, we compared the data read and written by Wukong and NumPyRen during the workload execution for TSQR. And as we can see, Wukong reads and writes considerably less data than NumPyRen, and this graph really helps to explain the performance difference between the two frameworks. It sort of illustrates the efficacy of Wukong's locality enhanced scheduling techniques and optimizations that result in a much less data being read and written during the workload. Keep in mind that the scale of the y-axis is logarithmic, and this just contributes to a much faster performance. And I have some other charts that'll help illustrate this as well. But first, we have here two graphs that show a CPU usage and cost comparison between the various frameworks. Looking at the chart on the left, we see the CPU usage of all the frameworks. Wukong didn't actually exceed 106 vCPUs or CPU cores during the workload execution. This is also for the same TSQR we've been looking at. This is because all of the tasks that Wukong uses are generally pretty small, or not that Wukong uses, but Wukong executes. They tend to be pretty small. So as Wukong scales up, invokes additional executors to execute these tasks. The old executors finish executing tasks and are reclaimed by the cloud provider. And this sort of forms a scheduling pipeline of sorts where lambdas are invoked, they execute the tasks, they exit, and it's fairly efficient. It doesn't require too much CPU. Similarly, we have this cost graph where we can see that Wukong single Redis ended up being cheaper than all of the other frameworks, especially NumPyRen. It reduced the cost compared to NumPyRen by a considerable margin, in part because it was slower, but also because of the way that decentralized scheduling works. We don't have long-running serverless executors like NumPyRen does, so we don't incur nearly as much cost. We also managed to be cheaper than both versions of Dask as well, simply just because we're not using as many resources. So now there's this question of how much does this data locality really make a difference with Wukong's performance? So to look at that, we have a chart on the left that shows an aggregate breakdown of the various activities performed by executors during a workload's execution. In this case, the workload was singular value decomposition for a 50,000 by 50,000 matrix. So with the optimizations I've been discussing disabled, we can see that the executors spend an overwhelming majority of their time performing network I/O. Task execution makes up a very small percentage of the aggregate time spent. And when we enable these optimizations, we see that task execution becomes a primary activity that's performed, and the amount of network I/O that gets performed decreases significantly. And this chart on the right helps to illustrate how much each individual optimization contributes to the overall performance. So we have this baseline chart that shows the execution time with both optimizations disabled and an intermediate storage. The intermediate storage is just a single instance of Redis. Once we add in a scalable intermediate storage layer, which we did in Wukong 1, we see that the performance improves by about 20.85% relative to the baseline. Once we add in the task clustering optimization we introduced in Wukong 2, the performance improves by about 48% relative to this multi-Redis cluster bar. And finally, adding delayed I/O results in another, I think, 46% performance improvement relative to task clustering. And to be clear, delayed IO, this bar also includes the task clustering and multi-Redis cluster. And the overall performance improvement when everything is enabled is roughly 4.6 times. So it's 4.6 times faster. So these data locality optimizations do make a substantial difference in terms of how well Wukong performs. So that brings us to Wukong 3. So Wukong 3 was designed to be completely serverless. That means there's no user-managed servers or virtual machines, and it can be run from a user's personal computer, like their laptop or desktop computer. This results in a very simple deployment process. We have lots of automated scripts that set everything up for the user. There's no management required during use. It's extremely user-friendly. But a lot of this was motivated in part because while Wukong 2 was fairly easy to use, we also provide automatic installation scripts and whatnot to simplify that process and to limit the amount of AWS knowledge you need. It still requires some AWS knowledge, and we wanted to make it as easy to use as possible. And Wukong 3 is still currently a work in progress. It is not a finished version. So the diagram on this slide shows the architecture of Wukong 3. As I mentioned, users can run Wukong 3 from their personal computer or on a virtual machine. It's up to them. A user will submit a program to the front-end client, just like with Wukong 2. Front-end client will submit this to a job invoker, which will invoke a DAG generating Lambda. The schedule generator from Wukong 2 was essentially converted to this DAG generator. This once again uses Dask to generate a DAG, and this DAG is passed to a bunch of Lambda functions. The way this works is that each leaf task in the DAG is assigned to a different Lambda function, and that Lambda function performs the depth first search from that leaf task. So instead of having the depth first searches occur in the static scheduler running on a virtual machine, they're distributed among all of the executors in the cloud. And this actually also helps improve performance of this stage. So after performing a DFS, the executors will begin executing tasks in the static schedule that gets generated. Now there's no intermediate storage layer, like there's no Redis in this version of Wukong. So instead, the executors communicate using a peer-to-peer protocol for the most part, and this is facilitated by a coordinator service. This coordinator service is currently runs transparently in the background on the user's computer or the virtual machine that they run Wukong from. They don't have to start it. Wukong does that for them. Users can opt to manage this coordinator themselves for performance reasons, like if they want to run it on a separate virtual machine, but that's not needed. The coordinator basically facilitates these peer-to-peer connections, and I'll explain that in a little more detail next. In some cases, executors can store intermediate data and metadata in S3. This is sort of a performance optimization. If we have like a really large fan out or a really large fan in involving a huge number of lambdas, it might be slow to do a bunch of peer-to-peer connections all to one lambda or from one lambda to a bunch of downstream lambdas. So to help mitigate that cost, they can just use S3 in a similar way to how they used Redis. And once again, when final results are completed, they're just returned directly to the user. So as for this peer-to-peer communication, I'll just briefly walk through the protocol that we use. The protocol involves at least 2 Lambda functions and this coordinator service. So the first step is the 2 Lambda functions send a connection request to the coordinator, and they pass a case-sensitive pairing key with this connection request. What the coordinator does is it looks at the keys that are being passed to it, and it'll exchange the IP address information between lambdas that connect with the same pairing key. So once the lambdas have received each other's IP addresses and ports, they're able to just establish a direct connection with one another as they normally would, just using like a socket API, and they can begin communicating by sending and receiving data. Beyond this, the design of Wukong 3 is fairly similar to Wukong 2 in its current form, so I will just briefly go over some of the preliminary results. So here we have the same TSQR results from before, but with a bar added for Wukong 3. As we can see, Wukong 3 outperforms the S3 version of NumPy for all problem sizes, and it outperforms the single Redis version of NumPy for all except the 262,000 problem size. Unfortunately, Wukong 3 is unable to achieve the same performance of Wukong 2, as well as the 125 worker Dask cluster. However, Wukong does begin to outperform the 1000 worker Dask cluster at the 2 largest problem sizes. I will get into the reasons for the performance differences here. So this chart on the left shows an aggregate breakdown of the activities performed by the serverless executors in Wukong 3. So as we can see, executing task code is the most commonly performed task by executors, which is good. But the next three most commonly performed activities shed some light on these performance issues. So we have AWS S3 reading, peer-to-peer receiving data, and peer-to-peer pairing time. So reading data from S3 is just reading intermediate data or metadata. This peer-to-peer receive time is the time Lambdas spend receiving on the receiving end of a peer-to-peer connection. And the peer-to-peer pairing time is essentially the time it takes the Lambdas to connect to one another. So while these activities aren't the most commonly performed activities by executors, it is the case that that they are often performed on like a single Lambda function towards the end of the workload because they have to aggregate all of the results that were computed in parallel at the beginning. So this just results in a lot of peer-to-peer connections happening back to back, and this ends up being fairly slow. As for cost, the chart on the right here shows the cost incurred by each framework for the 60 million problem size. We can see that Wukong 3 is cheaper than both versions of NumPyRen. However, it is more expensive than Wukong 2 and the 125 worker DAS cluster. This is largely because of the extra time spent establishing these peer-to-peer connections. It ends up just taking too long and it costs time because they're not able to do too much if they don't have, they can execute tasks at the same time, but otherwise they're just sitting there waiting, and this just needlessly incurs cost. So that is the subject of future optimizations. So to summarize the contributions of each version of Wukong, Wukong 1, we were able to create a serverless oriented DAG scheduler, DAG computation engine. We were able to provide competitive performance against serverful Dask, or those were our goals, I'm sorry, and we were able to do that. We were able to provide competitive performance with serverful Dask, and our decentralized scheduling technique enabled us to rapidly schedule tasks across a bunch of executors. This addressed the first challenge I identified, but as I mentioned, network I/O made up a bulk of the execution time, and this failed to address challenge 2. So to that end, we wanted to resolve the issues of challenge 2. We wanted to reduce network I/O, we wanted to increase data locality, and we wanted to demonstrate the efficacy of decentralized scheduling over these other serverless scheduling approaches. And we were able to do that. As for the specific numbers, we were up to 68 times faster than NumPyRen. We reduced network I/O by orders of magnitude, and we achieved up to 92.96% tenant-side cost savings compared to NumPyRen, thereby addressing the first and second challenges. We were also relatively easy to use and simple to set up with the provided installation scripts. That was a step towards solving challenge 3. But as I said, the deployment still required some knowledge of AWS, so we wanted to fully address challenge 3 with Wukong 3.0. We wanted to make it completely serverless. We wanted it to be as easy to use as possible. We succeeded in that respect. There are no user managed servers required, and it is extremely easy to use. It is extremely easy to use, but its performance and cost effectiveness are currently worse than Wukong 2.0. And to that end, we have some future work. And the first thing on that list is to improve peer-to-peer performance. There was a system called Boxer published in CIDR 21, where they provide a different system of doing this peer-to-peer connection between Lambdas, and their results appear to be better than the system we use. So one of our goals is to integrate Boxer with Wukong 3. We'd also like to extend Wukong to adopt a more generic programming model. So if we could remove the dependency on Dask and DAG inputs, we could support a much wider array of applications and optimizations. We'd also like to potentially explore creating a serverless supercomputer of sorts. So if we combine Wukong with InfiniCache, which is another project I worked on, then we could create this fully serverless supercomputer. InfiniCache is a first of its kind in-memory object cache that's built using serverless computing. So we would have a compute and storage substrate, both of which are built using serverless functions, allowing us to create this fully serverless computer. We'd also like to explore some new applications of decentralized scheduling, explore using it in different contexts, such as metadata management for distributed file systems. That's actually something I'm currently working on. AWS also increased the resource limitations of their serverless functions in December of 2020. This would potentially allow us to complete bigger problem sizes and also be faster. So we'd like to possibly take advantage of those. And finally, we'd like to potentially create a serverless benchmark suite. So if we can collect results from any real-world applications and workloads, we could conduct a first-of-its-kind workload analysis and potentially use machine learning. We could apply machine learning models to the data we collect to help improve scheduling decisions or develop further optimizations. But this concludes my presentation. Source code's available there if anyone wants to look at it. And yeah, thank you. So I guess at this point, we move to questions.
Yeah, thanks, man. Any questions?
Sure. Liz, you want to go ahead or?
Go ahead, I'll ask after you.
Okay. So about Wukong 3, you let's backwards since you just presented. For Wukong 3, like one of the major issue there is about this P2P pairing. Yeah. How did you do the P2P pairing here? Can you do that sort of like, because like I suppose pairing can be done in advance instead of like, upon the communication demand?
Yeah, that's a good point actually, because that is one of the ideas that we had, and it's not something that we've actually explored fully yet, but doing it in advanced is actually a really good idea. Yeah. So we use a technique called NAT hole punching. So cloud providers, or at least Amazon, typically prohibit inbound network requests to Lambda functions. They have it set up so you can't really do that. But you can use this technique called NAT hole punching, which just uses a name server to help the different Lambdas discover their public IP addresses. If you use this, then the Lambdas are able to communicate. So that's how we're doing it. I don't remember exactly how Boxer works, but it's slightly different, and I guess it's more efficient. This NAT hole punching thing uses a protocol called UDT, which is sort of like TCP. It's built on top of UDP. And it was developed by the creator of AWS Lambda. I forget his full name, but I think his first name's Tim. And the pairing ahead of time is something that could work. The issue with that approach that we haven't fully explored yet is just potentially the cost. We'd have to figure out a way to sort of intelligently determine when to do this pairing so that the Lambdas weren't waiting for too long, just incurring cost. But if, we found the sweet spot of starting them soon enough, then that would get rid of this pairing time, and that would potentially improve performance. It just depends on making it so it's not too early.
Okay, sounds good. So for the Boxer, you are not, that would be like my question as well, like how did that improve? But given you already mentioned that, I probably can look up look at the paper anyway. So another part of the cost is about the P2P data received. How is that done right now?
So how you're asking how the peer-to-peer data receiving works?
Yeah, because you showed on the picture that that's another major source, right?
Yeah. So the executors in Wukong 3 have been written to be asynchronous. So all of the network IO operations happen asynchronously. So when they start writing data, they're able to still perform, execute task code, and that goes for reading data as well. So as long as executors have something to do while they're reading and writing data, they'll do it in the background. But otherwise, the executors just they just basically sit waiting for a socket API to return. They just sit. It's kind of like a select operation. But it uses the UDT protocol, so it's a little different. But they're basically just waiting for a socket to, like, the buffer to fill up with data, and then they read it.
I see. But in general, like between like between two nodes, how many parallel connections do you actually allow?
So in my experience, there isn't a limit. We haven't set a limit, and there isn't a limit in terms of what they can support. But typically, it's usually just like one at a time, unless it's a fan-in operation. If it's a fan-in operation, then it just depends on the size of the fan-in, but there's no limit.
Okay. Yeah, I since like this P2P received data is sort of like another source, major source. What have you considered to improve that?
Yeah, there are a bunch of techniques that I had sort of have that I was working on before, but we sort of switched gears. For one thing, there's a question of using S3 to like better leveraging that in order to avoid the situations I mentioned where you have like a bunch of peer-to-peer operations that have to be processed by a single Lambda function, because that can be kind of expensive. And there are also other ways that we might be able to just eliminate this, eliminate the network transfer altogether. Like there's a feature in Wukong 3 that uses like a cluster mode. So instead of using Wukong the traditional way, it's sort of more like NumPy where you have like these long running executors that they can burst out the same way Wukong normally does to other executors. They can quickly scale up. And that sort of allows the executors to accumulate more intermediate data in their caches. So a lot of our techniques right now just sort of involve coming at it from that end, like just eliminating the data transfer wherever possible. It's also the case that just the network bandwidth is fairly limited. So we're just like transferring data is just something we want to avoid, I guess. That's like the name of the game right now.
Okay, I see. I'm just yeah. That makes sense. Okay, so for the coordinator you developed in the Wukong 3.
Yeah. Yes.
And did you use what kind of did you use like a sub pub or like a queue or whatever?
So the way it's implemented right now, it basically it's just a TCP server that the Lambdas connect to. The pub sub model is something I think I tried at the beginning, but I basically modeled the coordinator after the sort of example that the developer of this NAT hole punching technique, they sort of gave like an example coordinator, and I modeled it after that. It's multi-threaded, it uses Go, and it's just like a TCP server, so the Lambdas connect to it, and they basically wait for the coordinator to respond when another Lambda has paired. So like if a Lambda pairs with a pairing name foo, it'll basically just sit there waiting for a TCP response from the coordinator. If it has work to do, it can work while it's waiting for a response. But it's just a TCP server. It doesn't use like a pub sub model or anything. It's just establishing connections and messaging that way.
Okay, but like in your evaluation, it's not the bottleneck anyway, right?
Oh yeah, that's a good question. So yeah, we did do a bit of experimenting to determine if the coordinator was the bottleneck, especially because a lot of the data that we initially connected made it look like the coordinator was an issue. So we tried a few different ways to see if the coordinator was the problem. For one thing, we tried running the coordinator on different virtual machines that had better network capability and larger number of cores. The coordinator also was originally written in Python, and the multi-threading support in Python is bad. So we rewrote it in Go, and that the multi-threading support there is a lot better, and we didn't really notice a performance improvement. Even if we scaled up the number of connections, we ran some like micro benchmarks with the coordinators, just sort of like stress testing it. So like throwing tons of Lambdas at it to make it pair, thousands of connections at the same time, and it was able to do it instantly. And I would record like how long I would monitor how long it was taking to do these operations, like to pair the Lambdas to process their requests, and it was all really fast. So it doesn't appear to be the issue. I couldn't get the coordinator to perform poorly, because all it's doing is just basically handling one request and sending like a single message, and that's all it does. There's very little processing it has to do. There's very little bookkeeping it has to do. It's fairly simple.
That's good to know. So my next question is, have you thought of any way to get rid of this guy?
Yeah, that would be nice. It's just sort of the problem with the way AWS currently supports the peer-to-peer connections. It would be nice to remove the dependency on having a coordinator. The way Wukong has been designed as a whole, it basically the performance of our framework sort of improves with AWS. So if AWS were to lift some of the limitations they have on network operations, that would make it so that we could drop the dependency on the coordinator. We've also tried using things, we've thought of using other like intermediate storage platforms like S3, like fully managed services that the users don't have to manage in place of the coordinator, but that it isn't as fast. We explored using like Redis pub sub at the very beginning to sort of mimic the behavior of the coordinator. We explored using an SQS queue in place of the coordinator, but all of those performed poorly. That being said, Amazon did recently release like a fairly substantial improvement to SQS in terms of its performance. So using an SQS queue to facilitate this sort of message passing and coordination could potentially be viable. Now that SQS, I think that it was like throughput improvement specifically, that might work. But we tried a lot of the options that we could think of, and none of them proved to be as fast.
So one possibility to completely eliminate this coordinator component is to, so this is part of the another ongoing effort that is part of the other project in parallel. So basically in that project, we try to completely eliminate this coordinator by offloading this coordination process to a somehow programmable API gateway, and this API gateway is a service provided by AWS, so that we can allow, we can add some sort of intelligence to API gateway, which further invokes a bunch of Lambda functions as coordinators to help facilitate this UDP or UDT connection establishment process. Yeah, so this is also kind of in proposal that we plan to actually kind of tackle this challenge.
That's good. That's good to know. It's just an interesting interesting point to discuss. Yeah, I think I asked many questions. One last one before I let you go. So if there is a Wukong 4.0, what would you do to what would you do to improve?
Yeah, that's a good question. The prospect of Wukong 4.0 is fairly exciting. I think the key things that we would be looking to do here is to implement that generic programming model that I mentioned. There are the benefits of a generic programming model are like there's a huge number of them. It's not just supporting a wider array of applications, but this dependency on Dask is inconvenient. I mean, it's nice that Dask provides these DAGs, but Dask was not designed for serverless computing at all. So in some ways, we're kind of held back by the DAGs that Dask generates and the way that Dask works, like the way their computations work and the way it expects intermediate data to be available. It's not designed for serverless. So if we can remove this dependency on Dask, we would be able to implement a much wider array of optimizations. We could design like under the covers, under the covers, like the scheduling could be done with a more serverless oriented way. We could handle intermediate data in a more serverless oriented way and potentially be much faster, and also while also supporting basically any type of application. The current thing that we're looking at there is a fork join model, because you can sort of think of the fan in and fan out operations in the Dask DAGs as forks and joins, like the fan ins are joins and the fan outs are forks, right? So there are lots of implementations of traditional like linear algebra algorithms and even some machine learning algorithms like or clustering, like k-means. There are fork join implementations of these algorithms. So it might be fairly straightforward to adopt that sort of programming model. We might expose a more robust interface to the user, but under the covers, everything would be scheduled in a fork join way. So that would be the key idea behind Wukong 4 is getting rid of Dask and sort of exploring the problem space that we can do with this generic programming model. Okay,
that's interesting. I think that like looking at the fork joins in might be a good point. Yeah, that's all from me for now.
Okay, well, thank you for the questions.
Yeah.
Hey, thank you for the talk, Ben. That's a lot of work you did. I want to ask a few questions kind of from the standpoint of say the user of this particular system, because
Sure.
It's, as you said, you need to know a little bit about AWS and those kinds of things. And so I'd like to assume I could learn these kinds of things without too much trouble. But would there be any benefit to me to choose 1.0 over 2.0? I mean, is there something more I have to know to get this performance speed up, or is 1.0 really just kind of your starting point that's just your demo project to some extent?
Yeah, that's a good question. The short answer is that Wukong 1.0 is more of a demo project, but the difference between Wukong 2 and 3 is a bit more interesting, at least in their current forms. I talk about this more in the thesis itself, but there are certain applications and certain problem sizes for which Wukong 3 actually does outperform Wukong 2. It's just that the general tendency is for it to be worse. So there is sort of a question of, am I willing to trade this performance of Wukong 2 for the ease of use of Wukong 3? I think depending on the person, they would be willing to trade the performance. Like, I think a lot of people wouldn't necessarily care, especially if it was cheaper or about the same price. If it was like, I don't know, several minutes versus like if it was like 2 minutes versus 10 minutes or something like that, you know, like the barrier to entry for AWS can be fairly steep if you have like no experience with it. So people like that would probably pick Wukong 3 over 2, for example. That's sort of an interesting trade-off.
Is the difference there IO versus computation intensity?
Between Wukong 2 and Wukong 3?
Yeah. So in what cases does Wukong 3 outperform 2? What are the characteristics of the applications?
Yeah, right. So it depends kind of on the DAG structure that you have. So if you have a DAG where the fan-ins aren't too large, as in the number of tasks fanning into like a single downstream task, if there aren't too many, then Wukong 3 can usually perform fairly well because it doesn't have this one Lambda processing a bunch of tasks or a bunch of peer-to-peer connections, like one after another, or even like all at the same time, because it's asynchronous technically. That's what slows it down. So for example, in the thesis, I think it was the SVD of a tall and skinny matrix. That DAG, the fan-ins, I don't think are as intense, as big as SVD2, for example. So that we see a difference in performance there, and SVD1 Wukong 3 is able to perform better. I think it just helps. The dependency on servers helps. There were also some interesting trends we saw with Wukong 3's performance. Like as the problem size was increasing, Wukong 3, the end-to-end time really didn't change. And this also sort of illustrated that the bottlenecks might have been just with sending this data back and forth, but like the amount of computation, as the computation increased, it didn't necessarily increase the end-to-end time. So in theory, if you kept pushing the problem size bigger and bigger, it's possible that Wukong 3, even for these other workloads where the performance difference is fairly significant, it's possible if you push the problem size bigger and bigger, Wukong 3 would eventually start to outperform Wukong 2 just because its scaling its behavior is a lot different. Like it just doesn't get much bigger as the problem size increases. It stays close to constant sometimes, which is weird. But I think it also
It's interesting though.
Yeah, it is interesting. And I think it illustrates that if we can, optimize this peer-to-peer connection process, then Wukong 3 could be like very fast while also offering like, the cost effectiveness and being like super easy to use. So there's potential there at least.
Can you go back to you had a 2.0 slide with the essentially kind of the patterns that you were looking for and optimizing on IOs something and
this maybe?
No, the actual patterns that you were looking for. I think I just saw it go by. Enter 2.0. I think it's that slide.
Here?
Yeah, there you go. The task clustering versus delayed IO. Yes. Just so you were kind of looking for particular patterns. So this pattern here on the left. So so again, was the idea to have all 4 of these tasks, A, B, C, and D, all execute in that same unit?
Yes.
Okay, so what you're losing in sort of parallelism, you're gaining because you're not passing data around.
Yes, exactly. Yes, that is the exact trade-off. Yeah.
I'm gonna make sure I was interpreting that diagram correctly. So it's kind of, were there any other patterns you thought might be interesting in terms of being able to optimize for maybe large fan-ins? Did that make any sense at all? Or
Yeah, the large fan ends do make sense, although especially in the case of Wukong 3, the general trend or trade-off that you identified, though, was a big theme of the paper for Wukong 2, this parallelism versus like trading parallelism for performance, essentially, or not parallelism for performance, but parallelism for like network IO. So a lot of the DAGs and DASK sort of use the two patterns here fairly extensively. It's just sort of a feature of DASK, I guess. There aren't like a ton of other DAG patterns. Large fan ins are just a bit easier, I guess, just because at least in Wukong 2, they're just writing all of their data to intermediate storage. It's more, I guess it's more also dependent on the size of the data being written. Like these fan outs here that we see, they're not an issue unless the task data is large. So it's not just a matter of the pattern that we see, but it's a matter of the pattern that we see and the size of the data being transferred, which is why like this pattern on the right was kind of challenging because we had this large object with sort of like a weird looking pattern that had like layers to it. And it was hard to figure out what to do with that. But there's just not a lot of other like unique patterns like these two, at least for the problems we've been testing, at least. They all kind of look like this. The differences come with like where the large tasks and the workload are really.
Now, again, I don't know a whole lot about AWS. I assume it buys you a number of things like fault tolerance and.
Yep. Yeah,
okay.
Lambda offers fault tolerance. The way we've implemented the executors is that task execution is idempotent, so it doesn't hurt anything if you redo it. And Lambda provides automatic fault tolerance. So like if something happens to the Lambda and it crashes, we can just re-invoke it with those tasks and execute them again, and it's fine. So it kind of handles failures on the Lambda side like fairly cleanly and automatically, which is nice.
Okay, well, thank you.
Mm-hmm. Yes, thank you.
Any other questions from students? Well, yeah, I don't have further questions either, but I'd like to add some, follow up a little bit on the discussion that we had. So as yet another future, well, maybe this was already mentioned by Ben. So as another future direction, maybe we may call it like Wukong 3.5 or Wukong 4 beta. So we're actually planning to port Wukong to Hopper, which is an on-campus high-performance computing infrastructure that uses OpenStack for virtualization and access and user admission service and whatnot. So an interesting idea is to basically port Wukong to this open testbed so as to offer serverless data analytics notebook service, such as Jupyter Notebook, without requiring users, on-campus users, including students and faculty, to worry about tedious administration overhead. For example, they are not required to provision their own distributed systems and everything, so that they can choose to provision a single container or this backend infrastructure would automatically scale by leveraging Wukong's elasticity. So this is another future direction. Yeah, and actually, the decentralized scheduling technique that Ben proposed is kind of generic in some sense, and that actually motivated another interesting idea, which was mentioned as this one of the bullets over here. Yeah, bullet number 4. So we could basically leverage this decentralized scheduling in a completely different context, which is distributed file system metadata processing. So we could take advantage of this elastic service computing's elasticity property as a very interesting extension to traditional serverful metadata processing in order to handle bursty and a small file intensive file system metadata workloads. Yeah.
Very, I mean, very interesting directions. Particularly the second one, applying to this metadata management. I would perceive probably there, I can't think immediately, but I would perceive there another set of interesting problems would pop up.
Right.
When you use this to handle metadata.
Yeah, exactly. Yeah.
Yeah. Yeah, looking forward to that.
Yeah, us as well.
Okay. So I guess I will just move the students and Ben's friends to the waiting room so that we can have a private discussion among the committee members.
You can stop recording now.
Oh, yes, good point.